Welcome to all that is on the new lecture that is on algebraic structures. So here we will discuss about the group and the monoid semigroup. So first of all, what is the algebraic systems? Actually, we have some sets, natural sets are there, means some basic sets are there. First one is, suppose we have the natural number set. All of you know that the natural number set, we have the elements are like 1, 2, 3, 4 and so on up to infinitive. So this is the set of all natural numbers. And if we have the set is Z, Z is the set of all integers, and our integers is like that 0 plus minus 1 plus minus 2 plus minus 3 and so on up to infinitive. And one another set we have the Q is the set of all rational numbers, and we have the set is capital R, that is the set of all real numbers. So we have some basic sets are there, and you know that what are these sets and how much which type of values in these sets. So what is the binary operation? Actually, in group theory we use the binary operation. What is the binary operation? The binary operator we denote it by this star. This is our the binary operator. So this binary operator is said to be a binary operation, or we can say that the closed operation on a non-empty set A. Capital A is denote a non-empty set. So when it is a binary operation, when it fulfill this condition A star means a binary operation B, where A and B are the elements of A belongs to A. So this is our the closure property, means if we have any set, we have the two elements that are belong to that set. So their operation, means that binary operation whichever is given in the question, addition, subtraction, multiplication, division, whichever you have. So all these operations, it will fulfill this condition A, that binary operation B is also belongs to the set A. So let's take an example. If we have the set, suppose capital N, and capital N, we know that the capital N is the set of all natural numbers. So we say that here this natural number set is closed if we take the addition and multiplication, means this binary operator is like a addition or multiplication, because when we apply the addition, so if we add any two numbers of the natural number, so we get again a natural number, right? 1 plus 2, 3 plus 4, any natural number addition, we get the again natural number, right? And if we talk about the multiplication, so always when you multiply any number of the natural number set, so you will again get the natural number set, right? 1 multiply 2, 2 multiply 3 6, 3 multiply 4 12, like that. But if suppose I say that this your binary operator is subtraction, so if you have, suppose you take any two numbers from the natural number set, so is it possible that their subtraction is must be lie in your natural number? No, because suppose you take the one element is 1 and second element is 2, so when we take the difference of these, so 1 minus 2 it become minus 1, but minus 1 is doesn't belongs to our natural number set. So we can say that our subtraction and like the division also, because when we divide 1 divided by 2, so that is the rational number, not the natural number, because our natural numbers is completely the whole numbers 1 2 3 4 and so on. So in the case of subtraction and division, this set natural number set is not are the closed set. Clear? Okay, so now what is the algebraic system? A set A with one or more binary operations defined on it is called a algebraic system. Like natural number, we have the two operations are there. It satisfies the closed property, addition and multiplication. So like that we have some examples. Natural number, it is our the algebraic system with addition and the multiplication. Like the integers, if we talk about the integer set, so it is also the closed addition, with addition and the subtraction, right? And real number is are the set, or we can say that the algebraic system, if in all the conditions, means addition, multiplication and the subtraction, so all these operators, this set are the algebraic system, right? You can check it. Okay, so now some properties are there for the algebraic structure. First one is commutative property. So what is the commutative? So let we have the binary operation be on a set A. So the operation is said to be commutative. When it is called the commutative in A, if we have suppose two elements, the set A and B, small a and small b, then if its properties will be hold, a star b is equal to b star a, so we can say that these this system or this binary operation hold the commutative property. Second one is the associativity. So if our binary operation on a set A, so this operation is said to be associative if we suppose we have to take now three elements A, B, C in the set A, so its property must be hold A star B star C is equal to A star B star C. If this property will hold, so it is the associative property. Now the third one is identity. What is the identity? If we have suppose A star is represent an algebraic system, so an element E in A is said to be an identity element of A when if it fulfills this property, A is any element of the set A, so A star E is equal to E star A is equal to A. If this property will hold, so we can say that the set has the identity E. Next one, and you have to remember this one thing is that if in your identity element, if suppose in any set you have the as exists the identity, so that will always be unique. Not like that you have the two identities of in any set. No, identity always be a unique. Now the inverse. Suppose A star we have algebraic system, then and with the identity is with E have, so let A be an element in A, then B element B is said to be inverse of A when if A star B is equal to B star A. Star is represent here the binary operation, remember this. So A binary operation B is equal to B binary operation A is equal to E. If this property will hold, then we can say that the algebraic system has the inverse. Means we can say that here B is the inverse of A and A is the inverse of B if this property will hold. Clear? Okay, so now come out the semi-group. So what is the semi-group? Which algebraic set we can say that that is a semi-group? So an algebraic system A star or A binary operation is said to be a semi-group if it fulfill these two conditions. First one is this binary operation is closed operation on set A, and second one is this binary operation is an associative operation for all A, B, C in A. In earlier slide I told you the properties, all properties of the group, so that is commutative, associative, identity and the inverse. So here what is the semi group? Semi group is that group which has the only these two properties. If any group has only these two properties, means closed property and the associative property, so that is called the semi group. So like an example, if we say that we have the natural number set, so natural number set and we take the operation is addition, so this is our the semi group, because in addition case of the natural number it will be closed and it is hold also the associative, so we can say that this is a semi group. And if we talk about the multiplication, I earlier told you that natural number with multiplication hold the closed property and the associative property, so it is also the semi group. But If we talk about the negative, uh, subtraction, means our operation is subtraction. So I told you that if we have the natural number set and we apply the subtraction here, so the two numbers we take from the natural number set, is it not possible that the subtraction of two numbers always lie between the natural number set? So it means that this is not hold the closed property, so it is not a semi group. Now come to the monoid. So what is the monoid? An algebraic system A binary operation is said to be a monoid if the following conditions are satisfied. So here, first one condition is that it must be closed. Second, it must be associative, and third one property is added here for the monoid in comparison to the semi group, that is it must have the identity. So one more thing if we added here, that it is an has an identity, so that is called the monoid group. Clear? So now we take some example for the monoid group. So here I have that we have to show that the set n is a natural number set, is a monoid with respect to multiplication. So how to do it? Let's see here. We have the natural number set, obviously, that is 1 2 3 4 and so on. So now first thing is that for the monoid we have to that our set must be the closed set. So we have to fulfill the closure property, and for the closure property we know that the two natural numbers, again we get the natural numbers. Like suppose we have the two elements in the natural number set a b, so and we have to take the operation is multiplication, so a multiply b is equal to always the b multiply a, and this is belongs to n, so it will hold the closure property. So we can say that our multiplication is a closed operation. Now second is associativity. So multiplication of natural numbers is associative also. So like that, if we take any three numbers of the natural number set, so all it is always true that a b, if we multiply two numbers and then we multiply the third number, or if we multiply the second and third number, after that we multiply the first number, so that will be the same. So we can say that our multiplication is associative. Now for the monoid, third thing is that we have to have an identity. So suppose we take that our 1 belongs to n, right? 1 belongs to n, 1 is the natural number, such that a1 a, if we take a any element from the set n natural number set, so a1 a multiply 1, if we do that, this is equal to 1 multiply a, and this is equal to a, obviously. So here this is the property of identity, that e is equal to a is equal to a, means if we multiply any number with the identity, so we'll get the same we'll get that number. So here this condition is fulfilled, it means that our identity is 1 here. So identity element of the natural number set is 1 here. So it holds these three properties, so we can say that our set n is a monoid with respect to the multiplication. Clear? Now come to the group. So what is the group? So here if we have an algebraic system G, and the binary operation is said to be a group if the following conditions are satisfied. So here we have much more conditions to must be a become a group. First one is a that operation is a closed operation, and that operation is an associative operation. Third one is there is an identity in that set, and fourth one is every element in G has an inverse in G. So here one more thing is has been added here, inverse. So if inverse is exist, so we can say that this is a group. Now next one is the abelian group, or you can say that commutative group. So what is the abelian group? So if we have a group, means first an algebraic system have a group, it means that it hold all these four properties. After that one more condition if it will satisfy, so it will be the abelian group. What is that? If this group, means this whole country which hold these all four properties, if a group is said to be abelian when if A star B or A binary operation B is equal to B binary operation A for all AB belongs to G. So if it holds this property A star B is equal to B star A, this commutative property it will be hold again. Next, fifth one, so it is called the Abelian group. So that group is called the Abelian group. Okay. So now when we have a theorem is that if in a group G with the binary operation hold these properties, identity, what are the properties of the goods, that is identity element is unique always in your group, identity will always be unique, and inverse is also an element which is unique, and cancellation laws hold good here, means cancellation laws will be hold here. A star B is equal to, we can say that A star C. So cancellation, what cancellation here, left cancellation law if we use, means left cancellation means we can remove A to A, so it becomes B equal to C. So here it means that we use the left cancellation law. Similarly, right cancellation law, if we have suppose A star C is equal to B star C, so we can write it A is equal to B. So here we apply the right cancellation law. Next one is, if we take the A star B A binary operation B, take the whole inverse of this. So it will be equal to B inverse binary operation A inverse. Excuse me. Now, in a group, the identity element is its own inverse. Always you have to remember that the identity element in the group is at always it's the inverse, always of its own inverse, on inverse. So now order of a group. What is the order? If we have a, suppose we have a group, so what is the order of that group? So the number of elements in a group is called the order of the group. Suppose in a group you have the 1, 2, 3, 4 up to 5 numbers are there. So you can say that the order of this group is 5. Now finite group, what is the finite group? If the order of the group G is finite, then G is called a finite group. Finite, it means that you have the some number of limits are there, not like the natural number, integers number. These are not the finite group, these are the infinite group, because we have the infinite terms. But if we have some finite number set, means suppose we say that your set is 1 3 5 7 9 up to this is your set, so you have here the fixed number of elements are there, so this type of group is called the finite group. Now let's take some examples here. Show that the set of all integers is a group with respect to addition. So here we have to show that our group is all integer group is a all integer set is a group in terms of the addition. So first we take the z. Z is our denote the set of all integers here. So integers, you know that you have the elements are what, which type of, plus minus 1 plus minus 2 plus minus 3 and 0 like that. So here we have, suppose take the 3 elements A B C R from the Z. So now first we hold the closure property to become a group. So closure property, in closure property, if we take some any two elements from the integers, so always you can see that in the case of addition, again you will get an integer. So here it's like, suppose A B elements we take from the integer, so A plus B is always belongs to the Z. So it will hold the closure property. Now second one is associative. So we can say that if we add three numbers, so this is will be associative. Suppose we take A, B, C, three numbers are there. So A plus B plus C, this is always equal to A plus B plus C in case of the integer. So we can say that, yeah, this is hold this associative property. What will be the third? Third is the identity. So identity in addition, you have to remember this. If we talk about the addition, so always your identity will be 0, and in case of multiplication your identity is the 1 like that. So 0 belongs to Z, and we know that our 0 belongs to the integers also. So we can take here, suppose A is element of Z, so A plus 0, then we get A. So it means that 0 is the identity of this set integer. Now inverse. To each a belongs to z, we have minus a belongs to z, such that a, when we you add, means because this is addition, so when we add the identity in any number, so we get that number. So a plus we get the identity if, so we can say that that number is the inverse of another number. So here if we take a belongs to z and another element we say, suppose minus a belongs to z, and when we add these two numbers a plus minus a, so it becomes 0. It means 0 is the identity. So when we add two numbers, so we get the identity. It means that we can say that a is the inverse of minus a and minus a is the inverse of a. It means that each element of z has an inverse. So all, if all these four properties will hold the our set, so we can say that that is a group. Now if suppose it will hold the commutative also, so we can say that this is a abelian group. So check that it is will be commutative or not. So here we take two elements, so in the integer set ab, so a plus b is equal to b plus a. Yeah, this is true. So we can say that because it hold also the commutative property, so we can say that our z integer set with the addition has an abelian group, right? Okay, so now let's take another example. Here we have to show that set of all non-zero real numbers is a group with respect to multiplication. So here we have to show that the real number set is a group with the multiplication, non-zero, right? So now again, suppose we here we take that r star is represent our the non-zero set of real numbers. So first property we will hold here, closure property. So in closure property we can see that the product of two non-zero real numbers is again a non-zero real number. You can check that. So we can say that a multiply b is always belongs to the real number if we have the ab belongs to r. So this is the closure, hold the closure property. Now come to the associativity. So always we can see that if we multiply three numbers, first two numbers, then multiply the third number, so that will be obviously equal to the, if we use the multiplication last two numbers, then multiply the first number, that will be the same. So suppose here if we take three numbers, a b c belongs to non-zero real number, so it property will hold, so it is fulfill the associative property. Now the third one is identity. So for the identity I will told you that I told you that in multiplication case we take the multiplicity is 1, identity is 1. So we suppose we assume that 1 belongs to our real number. Yeah, obviously 1 belongs to real number. And if we take any element of the non-zero real number set, so when we multiply this number with 1, so we will get the same number. So it means that 1 is the identity of this non-zero real number set. Now fourth one is inverse. So if suppose we take a is any real non-zero real number set, and suppose we say that 1 upon a belongs to real number. Yeah, it is obvious that because we have the real number set, and real number may be anything, we have the real number. So 1 upon a is also the real number. So when we multiply these two numbers a or 1 by a, so we get the 1, and 1 is our the identity. So it means that we can say that here each element in non-zero real number has an inverse, right? So it means that this is a group because it holds all these four properties. So we can say that our non-zero real numbers is a group. Now check the commutative. If it satisfy the commutative, it will be a Abelian group, otherwise not. So when we check the commutativity, so here suppose we take two elements from a non-zero real number, so obviously the multiplication means a multiply b is equal to b multiply a always. So it is hold the commutative property also. So we can say that our non-zero real number with the multiplication is an abelian group. So clear how to verify that our group is abelian or not? Okay, so now if we have, suppose this type of example is there, we have to show that set of all real numbers. not non-zero real numbers. All real numbers R is not a group with respect to multiplication. How is it possible? So here you can see that we have 0 belongs to R, right? Because all real numbers we have to consider in this set. So 0 belongs to R, but you see that multiplicative inverse of 0 doesn't exist. Why? Because it is not the possible. This node doesn't exist. 0 multiplication inverse in multiplication it is 0 doesn't exist, because 1 by 0 is infinitive, not defined. So we can say that our R is not a group because it has not the inverse. 0 inverse it doesn't exist. So it is say that R is not a group. So any one property from all these, if it is not hold any property, so we can say that this is not form a group. Okay, so now let's take another example. Here we have the set Z. Z is the obviously the integer set, and with operation binary operation be an algebraic structure where Z is the set of integers, and this operation, what represent this operation, is defined by n star m. This is equal to maximum of nm. So it means that it is star means that binary operation is like that. If we have the two numbers nm, then maximum of nm. So now let's verify this. Uh, we have to show that here this is a semi group actually. What we have to show here, we have to show that this is a semi group. And next one, we have to find that is it monoid also or not. So now first, for the semi group, what properties we have? To become the semi group, we have that the set must have the closure property and the associative property. If it hold both these properties, so we can say that that is a semi group. So if we take suppose three elements A, B, C belongs to our Z, so closure property, if we talk about the closure property, so we assume here for all A, B belongs to Z, A star B, a binary operation B, what is represent this maximum of AB. So obviously if we take two elements of A and AB from the set Z, so obviously the maximum of anyone, whichever is A or B, so that is also belongs to Z, so it holds the closure property. Now come to the associative property. If we take three elements A, B, C from the set Z, so it must be hold that A star B star C is equal to maximum of A, B, C, both are equal. So it holds the associative property, so we can say that our Z and binary operation such is a semi group. Now check the monoid. So for the monoid group, we have one more condition we have to satisfy here. The which one is identity. If it holds the identity, so we can say that it is a monoid group, otherwise not. So check here the identity. Here we have that there is no integer x. There is no integer x such that what? That suppose we take a element from the set Z, so a is binary operation x, that is maximum of ax is equal to a. So is it not possible that if we take the maximum from the set any element a and x, that is always a, it may be x. We have to take the maximum from a and b, so it may be x. So not doesn't always that it is equal to a, means that is are the uh, means we can't say that x is a or are the identity, because this is not hold the property of this that we get always a number. So here our identity doesn't exist, so we can say that Z star is not a monoid group. Clear how to show it? So today's lecture is completed now. Thank you.